So my topic, microsystems integration, I'd like to approach that topic by looking first what kind of trends are driving the development in this area. What are the challenges with the materials compatibility, different materials compatibility, and what is the development flow that we are using for microsystems development. So we think that we already have quite a bit of electronics around us, but yet more than 90% of the objects and devices around us do not contain electronics yet, and that will definitely change. And we will have those embedded all over in all the objects surrounding us, even in ourselves. Then those devices which already have very high electronics content will continue go strong, and quite extreme example of that is obviously autonomous driving, which will require, in order to function safe, very high amount of microsystems. Internet of Things is not going to take place in internet only, so obviously we do need interfacing devices, analyzing devices, on all those connected vehicles. So what is a microsystem? So we do have sensing functions, we do have some analyzing, processing functions, we do have some actuating functions, and quite seldom this, depending on the application, will certainly be distributed differently, but quite seldom all of them can be integrated monolithically. That means within one piece of silicon or another semiconductor. So typically what you will have is what we call heterogeneous integration. So all those technologies for power, for sensors, for other analog functions, for digital, they are very different, and the cost of manufacturing is so different that we want to keep them separate, even though it would be technically possible to integrate more on a single piece of semiconductor. So we end up with something like this. And that now looks like a reasonably complex system on perhaps a circuit board. What we have here in the middle, we have different kind of components on both sides, and they are interconnected through the board. Well, this could be a size of a credit card, perhaps. But if we looked at those future applications, this is not going to be enough. So you want to have, in many applications, all of that and perhaps more to be integrated in a size of a thumbnail, so a 1 square centimeter. So what we do, we would pile all of them up and interconnect all these different devices through silicon. So this, or the semiconductor, whatever technology is then selected. So in this case, I would have here a MEMS sensor and a control die, and those are communicating with each other through wiring, which is going through the silicon. Looks like this. This is a copper filling, so there are etched paths around 5 to 10 or 20 microns max, and going through perhaps 100 microns or more. And those, again, will have a very delicate structures. If we go, we will have all the isolating structures and diffusion barriers and so on included underneath. Another direction, flexible electronics, not always. We want to have everything in a very small area. We might want to have the electronics spread in a large area, in fact, but it should be invisible, it should be flexible, it has to be integrated in the fabrics or in clothing. And for those, the combinations, usually we are embedding the electronics within organic substrates, perhaps, like the early examples are now doing. We might stack them then within the substrate, within the organic substrate, or we print it even on the paper, the electronics, and laminate the electronics content between the sheets of paper. And we will continue this heterogeneous integration to very extreme. What can we get out of materials, dissimilar materials brought very close to each others is actually metamaterials or nanoscale composites. So if we are not happy with all the material performance with the existing materials, we can generate materials that doesn't exist as such. So we can generate periodic structure with sub-wavelength dimensions, like here, either by periodic layering or by sort of array structures, and generate then controllable properties which is not defined by the chemistry, but rather by the structure. And obviously these are more known today in the optical or terahertz applications. Invisible cloak, perhaps the most known example of that, but those are also interesting for other applications like mechanical or thermodynamical applications, having perhaps an non-linear mechanical behavior and similar. So all of that, let's go now these trends in mind, go back to whatever the microsystem would be today. Looks quite nice. We have lots of opportunities. How do we do it? We just buy latest equipment from the market and do this. No, it's actually quite challenging, because what we're having here is if you zoom from any of these microsystems further to one component level, and then just in any place of the component we zoom again and take a look under the microscope, what do we see is actually a really composed of layers of thin layers of dissimilar materials. And then we are typically carrying these kind of devices around. We are not keeping them in a constant temperature in an isolated environment, but we carry them around, we drop them down. They will see high temperature, they will see low temperatures, they will have moisture around. So the conditions are quite challenging. And then some of the materials that we're using in such an assemblies happen to be such that they evolve during processing operations. So whatever you had in the first place after the fabrication might not be any longer there after some period of time of operation. So let's take a little bit more detailed look of these challenges. So first of all, this is from a materials point of view, this is actually a nightmare. So you really take all distinctly different materials. You take ceramics, polymers, metals, semiconductors, and you place them in a very small space together and expect them to work in a very demanding environment. And that is quite difficult because the mechanical properties of such materials are distinctly different, and when we expose those to high temperatures, for instance, just alone the fact that the materials expand differently will generate high stresses in between those materials and in design discontinuities. And the other problem is that we don't have a thermodynamic equilibrium state because we have these layered structures. So as soon as there is any, the kinetic prerequisites are met, reactions will take place, and the structure will change. And how would that look like here? For instance, an example, a material, this is a solder material in the beginning, it looks like a very nice and fine structure, and after aging, the structure has become a very coarse. And the issue with that is that even if the design engineer made a good job and he left a safety margin between the strength distribution of his system and the stress distribution that this device has to take, after time with this deterioration of the strength, those two distributions will overlap, and that is where our failure occurs, and then the system looks like this For instance, here some quite typical examples of different places where in the microsystem our different materials and interfaces come together. These type of failures at the interfaces and design discontinuities. That is what we will see in praxis. So how should we develop? How should we avoid such issues and be sure that also after 10 or 15 years those complicated microsystems will perform like they should? This is what everybody says they're doing, and okay, we do some modeling, we model our system, we do an experiment, we do testing, not only the operational testing, and not only the operational characterization, but also reliability testing to look at the aging behavior of, of that system. We do a failure analysis, and that's what we do. And I would say pretty much all the companies do not do this, and even, sadly, quite many research institutes do not do that. And what they compromise is modeling and failure analysis. And instead, I would call their approach is a trial and error. So actually, they do is lots of statistically well-designed design of experiments, lots of testing, some analysis, and back to the design of experiment. And in this way, you will finally, with this kind of a iterative approach, finally get this to this sweet spot, and that will function. If we look at this combination, different materials and design and application conditions. So they will find the sweet spots where this microsystem will work. The problem is that none of the system will stay as it is, almost none of them over the whole lifetime. So the manufacturer wants to change the materials, or there will come some design tweak, some additional features coming inside, or we want to use it in the different application. And then, if it doesn't work, if you didn't understand in the first place why did it work or didn't work, you will start again this very tedious experimental evaluation, which is going to take very long. So what should we do instead? And we have good tools available, which should be used consequently for microsystems development. And there is exactly those two areas, so the understanding the mechanical compatibility and the chemical compatibility. So chemical compatibility you can understand with thermodynamic modeling. You can, in a sense, model the chemical reactions taking place in a certain, at the certain interfaces. We have to take into account also how fast the reactions happen in order then finally to estimate something. But those two combined, and then we have to do a stress and strain analysis in order to understand the mechanical compatibility. So which areas are going to have which areas are in danger of having damage. And we should do a very careful microstructural analysis to understand the phase development, what phases we do have after the manufacturing processes, and also how does the microstructural evolution impact that microstructures. And so the interplay between these different tools of thermodynamic modeling, diffusion kinetic modeling, mechanical modeling, and the microstructural evaluation, microstructural analysis, this is how we can really develop permanently high-performance systems. So this is what what we in my team we are doing. We're combining different kind of modeling for the design modeling of the mechanical compatibility, for the thermodynamical modeling of the phase of the chemical reactions. We do whatever integration of the microsystem, so the experimental work actually, do reliability test, but not only test, we also develop new tests because sometimes we do have sometimes the single tests only on temperature or only on vibration are not giving the realistic conditions, and we're combining some of those standard tests to a new type of tests. Or specifically for sensors, here's a lot work to do. So microstructural analysis and really understanding the failure mechanisms in the integrated systems. And then, if needed, you would need to go back to your model and define that again before we then build a new experiment. So this is just one example of our work in the area where we are developing diffusion, solid bonding, solid-liquid interdiffusion bonding for this is used in MEMS sensors and also in power devices. And we can actually, by utilizing this called here Calphad method, but the modeling of the chemical reactions, we can design, we can find the optimal methodology, we can design the bonding area such that it will be able to take whatever stresses are focused on that, and also to keep it in high reliability over a very long time, over the lifetime. So with that, my conclusions. So there are quite interesting new materials, and also we have very interesting studies on two-dimensional materials, such as graphene. But really, in order to make those into innovations, they have to be integrated with something. And the multi-materials compatibility is very central to master such future microsystems and even going towards nanosystems. And development really requires a consistent application of scientific methods and predictive engineering instead of this trial and error method. I'd like to thank you for your attention.